Okay, then let's get right into the first talk, which is going to be by Fedor from JetBrains Research on the Arend theorem group.
Thank you. I will speak about the Arend theorem prover developed at JetBrains Research. It's one of the few interactive theorem provers developed specifically with the univalent foundations and homotopy theory in mind, and it's far from being experimental or something or anything like this. It has been developed for about 10 years and has many features and quite developed standard library and so on. Let me start with a brief recollection. Sorry? Okay. Yes. Okay, so let me start with brief recollection. What's univalent foundation of mathematical theory? I'll go quickly through it. You all likely know there's something about this. Univalent foundations of mathematics were formulated by Vladimir Voevodsky between 2006 and 2009, although many people took part in it. The term invariant foundations was coined by him. The central idea is that homotopy types are primitives there rather than sets. That was quite revolutionary idea. And the inspiration was by homotopy semantics of Martin Löf's type theory, where we interpret type of the equality type, intentional equality type, as a type of path. If you take type A, the equality sign between A and B is just a path between A and B, and then we can construct some higher level thing that would be a higher type of homotopies, and etc. This interpretation suggests certain axioms. One of the central axioms is univalence axiom, which you can interpret if you think more set theoretically as a principle isomorphic structures are equal, or like if you rather think in terms of infinity topoi, then it's something like object classifier. And then there are high inductive types, which are inductive types with normal constructors plus high pass constructors, which introduce some equalities, generate inequalities, and these are set theoretically. You may think of them as quotients, or theoretically or topologically suitable complexes. And there are two ways to approach normalization using such a formal system. One is synthetic homotopy theory, which utilizes the rich homotopical structure on types provided by equalities. For example, we can define circle as a high inductive type with constructor base and loop, introducing equality between base and base, and so this is advantages. For numbers of reasons. For example, formal proofs in this case are rather short and close to textbook proofs usually. For example, there is a very nice example of proofs that univalence applies. But that a fundamental group of circles integers, and it also has potential to reshape certain areas of modern mathematics by adopting a categorical perspective, so that you had assume you had some definition using sets, and you well, think more about it from different angles, and then you come up with some categorical structure, which is maybe cleaner or better behaved and so on. So, but there are some limitations. Original homotopy theory can't express general infinity categories, unfortunately. So types here are just infinity groupoids. We need some kind of directed code on this sector area for research. And then, well, there is set theory embedded in homotopy theory in form of H propositions, which are by definition types satisfying proof or elements, or as H sets, which are types satisfying uniqueness of identity proof, or in other words, such that quality is H proposition. So, this kind of set theoretical fragment is some kind of extensionally behaved set theory based on types. So it has quotient, functional propositional extensionality, structural identity principle, and etc. So what are available options right now for this kind of foundations? So we can use purely axiomatic code in mainstream interactive theory provers, like CoCagda. Well, not lean because it has some contradictory assumptions in the core of it. But well, the bad side, the inconvenience that are linked to it, although they have very developed infrastructures, is that it badly impairs computational content and MLTT of Martin-Luther theory, and normalization quickly becomes very, very cumbersome. So there are fully computational ITPs on the other side based on cubical type theories like cubical AGDA, but well, they are cubical type theories are sophisticated two-level theories and inspired by like constructive models in cubical sets, which one might think that well, practically, although it's of great theoretical interest, maybe practically one doesn't need all these computations. Maybe practically we can just go with something simpler. And the programmatic approach is the first approach. Taken by Arend, alternatively we can focus just on practical aspects. So we need as many computation, as much of computation as is useful in practice, and also like some nice features and so on and so on. Let me quickly run through the main points about Arend. So, as I already mentioned, development started about 10 years ago at JetBrains Research. Its type theory is just mild extension from LTT with interval type, which is type, not a free type. High inductive types are just inductive types with some conditions. I will explain what they are a bit later. Arend supports a quite powerful system of recursive classes with partial implementations and anonymous extensions, and also built-in type for arrays, which are simultaneously vectors, lists, and functions from finite set to I. Well, we have rich tooling with lots of features for Arend provided by IntelliJ IDEA plugin. Well, Arend is fully constructive. It doesn't accept exclude middle or axiom of choice, nothing like this. So the main part of Arend Lib is just constructive mathematics development of constructive algebra and topology, then a smaller part syntactic homotopy theory, and some bits of computer science. In the near future, we plan to support also directed codes, and then start some synthetic formalization, broadened synthetic formalization. So let me briefly sketch the basic construct. So the interval is inductive type is left with two constructors. We have something like cubical transport for it, or operation which you can think of as eliminator, which is called Koya. So it's we do pattern matching on this interval variable, and which is in general prohibited, and say that, well, if you have something on the left side, it defines the whole function, and we get something at every point. So well, almost all computational rules, I will give one rule later, is just as listed. So very natural rules saying that, okay, on the left it computes to A, and it's just A if I is not binded. So we can define paths that are type, again, so it's something built in, which is just a function from interval with fixed endpoints. And then a primitive operation that also some kind of eliminator that evaluates paths at some point of interval. And the Univalent axiom is just a function ISO which converts isomorphism or equivalence to equality, constructs a function from interval to universe. Well, there is a computational rule, just one, that computes square applied to is some, well, in an obvious way. It says that, well, if you do a transport on ISO, you just apply your isomorphism. So we have, let me give some examples. There is quality, identity. We have function extensionality, which is trivially proven here. Then standard function primap mapping, quality of arguments, the quality of images, and just standard classical transport along equalities. So we can derive eliminator GA using well, some elementary operations on this path on interval. This kind of definition satisfies standard computational rules, expected rules for J, which was an issue for cubical type theories. All those at some point resolved, but here it's rather trivial. And then there is pattern matching on IDP, nice feature. You can define functions by doing pattern matching on the paths. And this is very, very useful. For example, the proof in standard library of generalized Lakers-Massey theorem would be next to infeasible without this kind of feature. When you have to write like explicitly all these J's everywhere, it's a nightmare. Instead of this, you can just use pattern matching and then it goes through. So, well, the operations inverse and composition now trivially defined with the pattern matching and the identity paths. And well, we have some nice computational rules for result in path algebra, for which which are quite useful. And okay, so let me now say something about inductive types with conditions. Well, I will define them by example, by giving a couple of examples. So, well, if you take type of integers, well, naturally, you usually we define it using two constructors, positive and negative, and we want them to merge for 0. And this is something you can specify in this language using conditions. So we say that well, negative 0 it just evaluates positive 0, and then elimination must respect this. This mechanism allows to define high inductive types using interval, just as this kind of inductive types with conditions, like as shown. So this data type sphere, well, the circle is just base and loop, which is dependent on interval parameter, and on its to endpoints it relates just to base. So, very simple idea. So, well, in particular, we can define preposition truncation, and here this path constructor is just inductive sugar. It's essentially it's just as was shown above, inductive type with conditions. So there is an interval hidden actually. So and there is a user level construction that it places this kind of data type in the universe, specific universe probe. And there is a quite nice feature. We can define truncations in Arend entirely without inductive types. Just we can declare inductive type to be truncated, and then its elimination is restricted to H propositions, and that's the end of story. So, and that's quite a useful feature. So there's something analogous for set, for universe of sets, and well, this in predicative universe of H propositions and H sets, they explicitly delineate set theoretical fragment, which is nice. So we have some syntactic notion for proposition and set, which also corresponds to like more semantic notion of H proposition and then H set as defined in homotopy theory. And also definitions can be made polymorphic on homotopy level. So there is homotopy level variables that can be used in definitions, and they work in a similar way as predictive variables, and the whole thing works as analogously to predicative polymorphism. So another very useful feature, which is not related to homotopy type theory, but which is rather independent and will be used in other contexts as well. So this is a class system with partial implementation. For example, let's take a semi-ring structure, which is given by distributivities and multiplication by 0, and then well, you say that this is these are your axioms, but then if you define class ring as an extension of semi-ring, as shown, well, you specify that you extended the monoid structure for plus to group structure, then you can actually derive these axioms. So and you can use well, you can say that you implement these fields, and then for this you need what's called partial implementations, and well, another name for this construct is manifest fields. That's what we have in Arend. Another example, well, a partners relation. I won't go into details that much. I would just say that if you have set with the partners, and then when you extend this structure with group structure, then you can simplify your partners from binary relation to unary, and partial implementations also help a lot. So the summary would be that, well, you can define anonymous extension. Also, just small addition that you can define anonymous extensions on the flies. That's another consequence of this, as shown. For example, we can have in semi-ring, we can define semi-rings on natural numbers, let's say, and just on the fly. And well, this kind of feature raises distinction between fields and parameters of classes. Another consequence is that well, you can have bundled hierarchies of bundled and semi-bundled definitions in flexible form, so that when you use multiple inheritance, you can glue things and you can share things. And there is also very useful tooling for this hierarchy viewer in IDE that allows you to navigate through the hierarchies and look where things are implemented and so on and so on. So that's very useful. And there is also the type of arrays, as I mentioned. So this is defined as a record, but it also supports pattern matching. There are some constructors, as you expect, for nil and next addition of extra element. Well, this record is also converted from request from a type of function, so it behaves also as functions from FinSet. So the example would be when it's very useful if we consider data for term. As shown, if we try just well, assume we have some functional symbols applied to some arguments, and we have arrays of these functional symbols. Then, if we try to describe it as inductive time which uses vector for arguments, then we run into certain programs with elimination. With arrays, we can well just use this this argument v as a function, and everything works fine. So this is some clarification. Yeah, before I finish, let me quickly go through a remark on the standard library. So the formalization is done mainly well with two principles in mind. So first, constructivism, and the second, the maximal possible generality. So, and things formalized include, for example, algebraic closures, which are more tricky in constructive setting. For they define countable decidable fields. Then things like Hamilton theorem, linear algebra over Smith domains, and Nakayama lemma, then topology and analysis. That includes topological spaces, locales, uniform spaces. Also, I should mention theory of schemes via locally linked locales. Locales because constructively they are better behaved, and for some other reasons. And well, of course, basic category theory. Then syntactic homotopy theory, a number of things there, and a bit of computer science. Yeah, I do not mention idea features, although they're very cool. They're very nicely described on the website with demonstrations. You can have a look. And yeah, there is a paper, the paper draft available online. It's not yet finished, but it will be finished soon. You can have a look there for more details on what I was speaking about. So that was it.
Okay. Thank you very much. Should have time for one or two quick questions. So you mentioned that you plan to implement also the directed version of homotopy type theory?
That's correct, yes, but yeah, this are very real plans for near future, but it's not yet completely determined of like what kind of syntax it will be. But
okay, thanks. Other questions?
So I was also wondering, I mean, have you so established meta theoretic properties like normalization?
Well, yes, it's a very good point. So not yet completely formally, yes. No, we don't know. Well, so yeah, we know that, for example, type checking is decidable. So that's
okay.
So that's nice. And for example, in Lean, it's not the case because of some features. So yeah, but yeah, we don't know.
Okay.
Well, there is some note on model of homotopy theory with interval. So yes, but as for normalization and other multi-syntactic metatheoretic properties, we don't know.
Okay.
Okay. Any final pressing question? No, then let's thank our speaker again.